Good morning. Next is reactions of benzene. Reactions of benzene. This is known as aromatic, electrophilic substitution reaction. Okay. Reactions of benzene. Usually benzene is giving what type of reaction? Aromatic electrophilic substitution reaction. What do you mean by aromatic electrophilic substitution reaction? Look at here, benzene. This is benzene. You can see that in all the carbon atom there is a hydrogen atom. Okay, I can take this hydrogen atom. In the presence of an electrophile, what do you mean by electrophile? Positively charged species. These are known as electrophiles. This we have studied. Positively charged species are known as electrophile. In the presence of an electrophile, or when an electrophile comes to attack benzene, what will happen? You get a structure like this plus H plus. That means here you can see that this is electrophile. This electrophile is attaching to the ring and a proton H plus is removed. That means E plus is attached and H plus is removed. That is what is known as a electrophilic substitution reaction. One electrophile is attached to benzene. Simultaneously a proton, that is another electrophile H plus, that is removed. That is what is called electrophilic substitution reaction. The incoming electrophile, positively charged species, will be attached to the benzene ring with the elimination of a proton. That means an electrophile is attaching and another electrophile is detaching from the benzene. This is what is called electrophilic substitution reaction. One electrophile is substituted with another electrophile. This is our external electrophile and proton, that means H plus, that proton, another electrophile is removed. Now examples of this electrophilic substitution reaction. First one is nitration. So reactions of benzene, first one is nitration. First one, nitration. When benzene is treated with HNO3, concentrated nitric acid, in presence of concentrated H2SO4, this is what is called the nitrating mixture. When benzene is treated with the nitrating mixture, what do you mean by nitrating mixture? It's a mixture of concentrated HNO3 and concentrated H2SO4. We get nitrobenzene. What do we get? NO2, nitrobenzene. This reaction is known as nitration. Reaction of benzene with a mixture of concentrated HNO3 and H2SO4. We get nitrobenzene. This is NO2 and here this is known as nitrobenzene. Now look at the mechanism of the reaction. So the mechanism of nitration. So keep it in mind, what is nitration? When benzene is treated with a mixture of concentrated HNO3 and H2SO4, we get nitrobenzene. Mechanism of the reaction. This is important. Mechanism. First step one. What is the first step? For the attack, we need an electrophile. So that is the first step. Generation of electrophile. Generation of electrophile. First we need an electrophile. Okay, generation of electrophile. Look at here. Here we have H2SO4, nitrating mixture is H2SO4 and HNO3. H2SO4 and HNO3, these two will react together. H2SO4 means it's a stronger acid and it can be written as H plus and HSO4 minus. It will dissociate into H plus and HSO4 minus. Okay, this H plus will be taken by HNO3. This H plus will be taken by HNO3. So what will happen? It will change into H2NO3 plus. Because keep it in mind, H2SO4 can change into H plus and HSO4 minus. Okay, HSO4 minus. This H plus will be taken by the lone pair of nitrogen. So nitrogen is donating its lone pair and will abstract this H plus. So H will change into H2. Since it is donating a pair of electron, it will get a positive charge. And what will be the other product? Plus what we get? H SO4 minus. This is we get H2NO3 plus and HSO4 minus. Okay. Now look at here. This H2NO3 plus will undergo decomposition. It will decompose. H2NO3 plus is unstable. It will immediately decompose, and what will happen? It will change into H2O. One oxygen from here and water plus what will be remaining? One oxygen is removed, so remaining is NO2 plus. This is our electrophile. This is the first step in the nitration generation of electrophile. H2SO4 plus HNO3. What will happen? H2SO4 will dissociate into H plus and HSO4 minus. H plus will be taken by HNO3. It will change into H2NO3 plus. Plus what will form? HSO4 minus. This H2NO3 plus is unstable. Immediately will decompose it and it will change into H2O and NO2 plus. This is our electrophile. Now step 2. So step 1 is clear. Now step 2. Step 2. Formation of arenium ion. That means carbocation, positively charged carbon, carbocation, and its stabilization. Once the electrophile is formed, what will happen? This electrophile will attack the benzene ring. Okay, so look at it here. Here is our benzene ring. Okay, here is our benzene ring. And this is our electrophile, NO2 plus. Then what will happen? Look at it here. One of the pi electrons. Okay, suppose this pi bond, this pi bond, in the presence of electrophile, this is positively charged species. It is pi bond, pi electron. That means this is electron cloud. So what will happen? This electron, this pi electron, or this pi bond breaks from this carbon. Okay, any carbon. Okay, it breaks from this carbon. Okay, it breaks from this carbon and will abstract NO2 plus. So what we get? So look at it here. Here you are getting a structure like this. Here is double bond. Here is double bond. This bond breaks from this carbon and it will join with the NO2. So here it will become NO2. And what will happen? Since the bond is breaking from this carbon is getting a positive charge. Correct. This is what is called arenium ion. This is arenium ion, positively charged carbon. The ring with a positive charge carbon, that is what is called arenium ion, or simply you can say that carbocation, positively charged carbon. Now you can see that this arenium ion can be stabilized by resonance. How it can be stabilized by resonance? Since here is a positive charge, look at here, there is a positive charge, what will happen? This bond breaks from this carbon and it will be shifted to here. Okay, this is the resonance stabilization. Okay, so therefore you get the next resonance structure like this. Okay, here it is NO2, here no change, and you can see that the bond breaks from this carbon and it will be shifted to here. Therefore, since the bond is breaking from this carbon, here is a positive charge. Okay, now in the next resonance structure, what is the next resonance structure? Okay, this bond breaks from this carbon and it will be shifted to here. So you are getting the next resonance structure like this. Okay, here it is like this. Here NO2. Okay, since the bond is breaking from this carbon and it is coming between these two carbon, here is a double bond, and since the bond is breaking from this carbon is getting a positive charge. Okay, or this can be represented like this. Since the positive charges keep on moving, delocalizing. Okay, you can show like this. Okay, Okay, this is here it is NO2. You can show like this. Here is the positive charge because the ring is getting a positive charge. Okay, this is the resonance stabilization of rhenium ion. This is the second step, formation of rhenium ion. So how the rhenium ion is forming? Once the electrophile is formed, what will happen? One of the pi bonds breaks from the ring and it will abstract the electrophile, will abstract the electrophile, and ring is getting a positive charge. That is what is called rhenium ion. That rhenium ion can be stabilized by resonance, and this is the second step. And the final step, so look at here in the last step. Third step, what is that? Loss of a proton. Okay, so here I am taking the last structure. This is the last structure. Okay, what is the last structure by resonance we are getting? So here it is like this. Here it is NO2, and here is double bond. Here is double bond. Here is a positive charge. Okay, in order to regain the stability of the ring system, actually this is unstable. This system is unstable. So in order to regain the stability of the aromatic system, what will happen? Here is a hydrogen atom. Okay, as you know that here is a hydrogen atom, because in all the carbon atoms there is a hydrogen atom. So what will happen? This bond breaks from this hydrogen and the bond will be shifted to here. So what we get? We get a structure like this. Here is double bond, here is double bond, here is NO2, and what is forming here? The bond breaks from hydrogen. So what will happen? This hydrogen, that means it is going as H plus without its bond pair electron. This bond is shifting to here, and here it will become a double bond, and the hydrogen is going without its electron. That means plus H plus. Clear? Okay. So we get the final product, nitrobenzene. What is removed? Another electrophile is removed. How this H plus is removed? Keep it in mind. In the first step, what is happening? H2SO4 plus HNO3. In that step, we are getting one HSO4 minus. There is a in the first step, H2SO4 plus HNO3. What is forming? H plus and HSO4 minus. Okay, HSO4 minus, and this HSO4 minus, this H plus will join with HNO3 and plus what is forming this HSO4 minus. Actually, that HSO4 minus will abstract this proton. Actually, this is what is happening. HSO4 minus, I will abstract the proton, then that time what will happen? The bond will be shifted to here. So what will generate back? HSO4 minus is abstracting a proton, and that means actually this H plus is in the form of we get back our H2SO4. This HSO4 minus abstract the H plus and it will change into H2SO4. This is the overall reaction, the mechanism of nitration. Okay, hope it is clear for you. Next is so this is the first reaction, aromatic electrophilic substitution. First example is nitration. Now second one is halogenation. Again, for halogenation also there are three steps. First step is generation of electrophile. Second step is formation of rhenium ion and its stabilization. And the last step is removal of a proton. Okay, so second reaction, what is that? Halogenation. Halogenation. Example, bromination. Bromination. Example, bromination. That means when benzene react with bromine Br2 in presence of FeBr3, what we get? We get bromobenzene. Here it is Br, bromobenzene. Okay, plus the byproduct is HBr. Look at here, what is happening here. What is the mechanism of the reaction? Mechanism. Step 1. formation of generation of electrophile, generation of the electrophile. Okay, which is the electrophile is here Br plus. How Br plus is generating? Look at here, Br2. Br2 can be written as Br plus FeBr3. FeBr3 means Br. Since ion is attached to 3Br, because this is more electronegative, this ion is getting a partial positive charge. Okay. So what will happen? This Br is having a lone pair electron. With the lone pair electron, this Br will make a bond with this positive charge ion. So what we get? We get a structure like this, Br, and here it is also Br. It is making a bond with the Fe. Here it is FeBr3. Since this pair of electron is donating to ion is getting a negative charge, and since the pair of electron is given, this Br is getting a positive charge. Okay, here first we are getting this intermediate. Okay, now this is unstable, and what will happen? Immediately this Br, this bond breaks, and this pair of electron, this bond pair of electron will be migrated to bromine. So what we get, this Br is free, and since the bond is breaking from this Br is completely, this is Br plus what will form? Br, Fe, Br3 minus. So you have to keep it in your mind, this one. So this is Br plus. So for stability, what will happen? This bond pair electron will be taken by Br plus. So we have positive charge is removed, and what we get? Since the bond is breaking from Br, this will change into Br plus. This is our electrophile. Plus what will form? Br, FeBr3 minus. This is the first step for generation of electrophile. The rest of these steps are similar to that of our nitration. Look at it here. Second step. What is the second step? Step 2. Formation of rhenium ion and its stabilization by resonance. Okay, again the same. Okay, benzene. Here is our benzene. Anywhere you can show. Okay. Plus what is coming? Our electrophile is Br plus. What will happen? This bond breaks from. You can show any bond can break from any position. Okay. The bond breaks from this carbon. Okay. And here it is. Okay. So what we get? We get a structure like this. Here it is like this. Here is no change. The bond breaks from this carbon. Okay, you can show like the bond breaks from this carbon, and so you can see that this is like this. Okay, now the bond breaks from this carbon and it is joining with the Br. Okay, so what will happen? Here is Br, and here is positive charge. This will also you can show, no problem. Okay, now how it is stabilizing? Okay, how it is stabilizing? Here the positive charge is on this carbon, then what will happen? This pi bond breaks from this carbon and it will be shifted to here. So you get a resonance structure like this. Look at it here. Here is double bond. Since the bond is breaking from this carbon, here is positive charge. This bond is here and Br is here. Okay. Now, okay, Br is here. Now, what is the next structure? Here is a positive charge. Then what will happen? This bond breaks from this carbon and it will be shifted to here. Then what will happen? You get a structure like this. Here is double bond. The bond breaks from this carbon and is migrating between these two carbons. So here is a double bond. Since the bond is breaking from this carbon is getting a positive charge, and here it is Br. Okay, or it can be represented like this. The delocalization of positive charge. Okay, here is the ring is getting a positive charge, and of course here it is Br. Okay, This is the resonance stabilization of rhenium ion. And the last step, what is that? The last step, third step, step 3, removal of proton. Removal of proton. Okay, you take this last structure, okay, this is the last structure, okay, here it is double bond, here is double bond, and here is a positive charge, and here it is Br. So as we have discussed, in this carbon there is a hydrogen, for stability what will happen, this bond, this CH bond breaks from hydrogen. How it is breaking from hydrogen? Look at here, here you can see that in the first step we have Br, FeBr3 minus, this we have. Okay, now we can see that this Br with its lone pair will abstract this proton. Simultaneously what will happen? This bond breaks from FeBr3. So what will happen? Then what will happen? This bond will be shifted to between these two carbon. Okay, or no need to make such complication. The bond is the CH bond breaks from hydrogen and it is shifting to here. So you are getting the final product. Okay, you are getting the final product. What is that? Here is double bond, here is double bond, here is a double bond, and here it is Br. What you are getting? Br bromobenzene plus what will be generated? H plus H plus. That H plus will be taken by, see, this is our first step by product Br FeBr3 minus. That means this Br will take H and it will change into HBr. That means this will change into HBr and we get back our FeBr3. Okay, this is a catalyst, like a catalyst. We get back our FeBr3 which we were used in the first step. Okay, and during this reaction we get bromobenzene plus what will form? H plus means that is actually HBr. Okay, that's all. This is the mechanism of halogenation, particularly this mechanism of bromination. Okay, thank you.